pleasure to see you everyone here. And Robert, thanks for having me, but also I may be able to solve your puzzle about, like Bettina mentioned, about computer scientists and physicists and so on. I'm a computer scientist, but I'm also an engineer and also a manager, but I'm also a physicist, and when I'm asked one choice question, there is no hesitation. It's clearly a physicist.
What did you vote in the question?
Obviously physics. I don't remember, but obviously physics, because it's so much deep-rooted. And by the way, for us physicists, it's less intimidating to go into computer science and to go into engineering when we work in this field. And I think the path that you did, going from computer science and starting to scratch the physics, I think it's much more, it requires much more courage. And maybe one point here, the time that I felt that this field is truly computer science and not physics is when I see so many people working in it and do not need to use H-bar anywhere in their work. So maybe out of curiosity, they go out and find out what is H-bar, but they don't need it. And this is when we move to computer science. So thanks again for having me. And I will speak a little bit about technologies for scale, which is what we, as a company, were formed to do from day one. We understood that we need this technology and we need it for scale. Today, and certainly when we were formed 4.5 years ago, it was kind of a playground, a very important playground, but still a playground. But if we want to look forward, and we heard it in the previous talks as well, we need to think scale, and this is what I want to have you in mind throughout this talk of mine. I will cover the principles of what my company was formed about, which is the separation between functional modeling and the actual implementation, which comes about for program synthesis. There are two sides to this. First is to identify the right modeling constructs for quantum computation, and second is the technology. And as a company, we are a technology company. What we bring to the world, whether we will succeed or not, is the technology, is how to take a functional model or a model of what the algorithm developer wants to happen, and how by technology, by automation, to make it an executable program on a machine. I will show obviously some results, and maybe at the end I will say a few words about who we are, depending on the time. Robert was kind enough to say that we can include a demo in the presentation. I prefer an open discussion here, but if there would not be open discussion, we may have time for a demo as well to show. So this is the theory behind what we as a company stand for. So suppose the person who wants to write down a quantum algorithm, a quantum application, whatever they need, they just want to have it. And the implementation space can be quite large. Implementation space, I mean the code that the quantum computer will actually execute. So the technology or automation that we see today is some sort of, sometimes it's called transpilation, sometimes it's called compilation, but from low level to low level. This is what we see today across the board. There is some speech about going from high level to low level in true fashion. This was actually discussed long ago in the quantum arena. Q-Sharp had this agenda, but it was never implemented in the right way, and so on. So going from low level to low level, you have a very low view from a mathematical point of view, a very low legal view of where you can go, because you must abide by the low level that you get. You don't know of the intended function of this low level code. Whereas going from a high level intention, telescopically, step by step into the low level allows you the true flexibility which the user required. Transpiler and even what is called today compilers would never take this picture into this picture without knowing that a few of the qubits here are auxiliary qubits, in fact. And there is no technology beyond what we are now developing which will actually take you from a functional model that is represented here into an equivalent functional model that is represented here in an automatic way, without the user specifying in advance what auxiliaries are used. So this is just one example. I will describe more examples of this. So there are two pillars of going from a high-level description by technology into low-level implementation. First is that we really need to identify the modeling constructs, and we heard this in the previous talks, whether it is a simple for loop or whether it is more complicated idioms used by any quantum algorithms. If we identify the modeling constructs, then the compiler, the technology, has the ability, the knowledge to deal with those constructs in a reasonable way. So there is no embarrassment. One should not shy away from understanding what do real quantum algorithms actually need. And the second, of course, is the technology of understanding those constructs and implementing them under the specific constraints that are in enforcement now. Now, we see in here this, I'm very happy, in the last very short time, last maybe 1 year, 2 years, not much more, we see many implementations of Shor's algorithm because people are starting to think this way. Up to until 2 or 3 years, there was no serious attempt or ability to actually implement the Shor algorithm. Now, not many people ask themselves why. The Shor algorithm is very, very simple. It is only 3 building blocks, which are all very simple. The Hadamard transform, by the way, Bettina mentioned the for loop around the Hadamard. You should not think of it as many H's over many qubits. You should think of it as a single function, a Hadamard transform, and this is what you would see in the Classiq platform, just a Hadamard transform, no for loops over there. Then a controlled modular exponentiation. This is completely classical in a sense. Modular exponentiation, and then the quantum part of inverse Fourier transform. Still, there was no implementation because this part here of a controlled modular exponentiation, people thought about it a lot. They wrote papers about it. We will see a few papers, but it was and is extremely difficult to implement, and people did not invest in this effort. And this is what we are here for. This is one example of identifying the constructs of how to implement this efficiently, and then using automation. So in a sense, the writers of the papers, the creative people, the people who are really in the field, will find a way to implement this correctly from a theoretical point of view. But then, through automation, takes those constructs and transform them into an executable quantum program in scale. This is what we do. This is where we are here. And now, to give you some impression, in the next few slides, I will show you what it means to do controlled modular exponentiation. So this is a 96 paper. By the way, the implementation zone paper arrived immediately after the thought of the Shor's algorithm itself. Everyone understood that the controlled modular exponentiation is the problematic issue here from an implementation perspective, and they started designing some complex understandings of what it means. So this is one implementation on paper using a lot of controlled modular multipliers, and each controlled modular multipliers would use some controlled headers, whether it is ripple carry header or whatever. So this is a controlled modular header. And there are many details there, therefore the paper gets, noticed, because there are many details that people should think about. And then if we go lower into the details, how to implement the header, whether in Fourier space or in real space, so people design on paper, addition transformations, and so on and so forth. So this would continue. I could share this presentation if anyone is interested. And then the first part of our work is to go over, the corpus of knowledge of quantum algorithms and understand what are the quantum idioms. What do people really need in order to implement on paper a quantum algorithm? So we identify some simple stuff like this. Sliding control structure, which you all identify. Sorry. And this is, Bettina mentioned the for loop overagent, so this is another idiom of gates, sometimes the same gates, sometimes different gates on 2 bits. And then some more complex structures, which appear in many algorithms. So a cascade here or a slide, but with a secondary structure. And more idioms such as those, and we implement those idioms in the modeling language. And then the modeling language, on one hand, allows the person or the algorithm developer to use those idioms in a simple way, and also without even any compilation can allow them, I would say, communication between 2 experts in a simple way where they both understand the language. But more importantly, from the perspective of this workshop or this conference, is to allow the automation unit to understand those idioms. It allows the developers to invest a lot of time on optimizing those idioms under constraints and create telescopically this Shor's algorithm structure. So this is somewhere in the middle of the flow from the simple Shor presentation or description of 3 building blocks down to the bottom. This is somewhere in the middle. So this is actually a real picture from a previous version of the Classiq platform. Today it looks nicer, but this is actually something that our user can actually write, and the automation will understand this graphical language. So I want to present here how close it is to what the people actually write in LaTeX in a paper. So now all they have to do is actually write it graphically for the automation to understand. And I thought I would give you some more examples, but I see that I won't. So this would be a graphical description of one of the steps of the Shor's algorithm that the user can present. And this would be the textual description at the same level. So this is still not machine code. It is much, much higher than machine code. So the user can decide whether they want each, I would say this would be the period function, each function to write graphically or textually. And now I will start to present the technology. As I mentioned, there are 2 pillars. First, understanding the idioms that the quantum developer thinks with. And second, to develop or create the technology which will take those idioms or high-level description into low-level code, but not by transpiling to very similar low-level functionalities, but by understanding that what the user needs, what the developer needs, is to be functionally correct, and not to be correct on any bit and piece because they don't care about it. So this is what you need to have in mind when I will describe the technology or the automation. So let's start with examples, and as usual, when we learn by examples, we will start from the simple and gradually grow. So let's look at the most common working horse of quantum computation, which is the multi-controlled gate, in this case multi-controlled X. So this is the function. What the user cares about in this particular case is that this function will be implemented. It has 6 control bits and one target bit in this particular case. It can also be controlled on zeros or ones, it doesn't really matter. And this would be a particular implementation of this function. It actually uses no auxiliary qubits. So the same number of qubits in the physical implementation as in the logical description is what the user wants. It has 168 CNOT gates and the depth of 225 in terms of CNOT gates. I believe it is optimized. We cannot do better, as far as I recall. And this is a different implementation of the same function. This would be a 9-qubit master implementation of the same 7-qubit functional multi-control knot. So here you trade off 2 additional auxiliary qubits if you have them for much less CNOT gates. There could be an 11-qubit master implementation, and so on and so forth. And in this particular case, anyone here coming from engineering, one of my other hats, by the way, I have so many hats because I'm just very older than you guys. When you reach my age, you will have at least as much expertise as me. So if we are looking from an engineering perspective, we just have a trade-off table, which is so common in any engineering EDA tooling. And we see that the machinery, that the automation, that the synthesis engine needs to trade off between the widths of the function in any particular point in the algorithm. I did not tell you where this MCX is functionally located in the algorithm. So at any particular point, the synthesis engine needs to trade off between widths, number of available qubits, memory if you like. Actually, the auxiliary qubits, it would be just the same. The number of CNOT gates, depending if the gates are noisy, depending if it is 2-dimensional connectivity, so any CNOT gate would require many swaps or not. So the number of CNOT gates, the qubit depths, and this for any function. We can go on to many more to functions which are larger. You see the point here. So this was one example. Let's look at another. By the way, questions, any discussions so far? Because I can go on to many. Yes, please.
On the previous slide, you were showing the implementation of the 7-controlled MCX with 6 CNOT gates, but that isn't even enough to entangle all of it.
This line might be a mistake.
Yes.
This line is a mistake. I'm sorry about that. It's an older version. You are correct. But the first 3 lines are correct. I'm sorry about that. Thank you for raising this up. Yes, please.
What now is it specifically what your technology does? Does it create this table?
So not necessarily. Typically, those tables would be input to the technology. The technology would look, it's not tables, it would be within code. Usually the code is not tabular, but functional code, which trade-offs between the different parameters. And then the technology will find the optimum, but here I want to stress the point. It will find the optimum, including it has much more degrees of freedom than a regular compiler that you would think about. It can recognize how to add, in this example, auxiliary qubits, even though the user did not specify that auxiliary qubits are part of the game. And I will show other examples where you will start noticing the large design space, the large freedom of choice that technology has. So typically those things, not in tabular form, but in trade-off forms, in a code, those are given. We provide them. We don't expect the user to understand them. This is where we did a very comprehensive understanding of the idioms of quantum computation. Obviously, multi-control X is one of them. We provide those tables of functions, trade-off functions, as part of the technology, but the actual technology, the end-to-end, takes those into account. And now, yeah.
Does the user have to specify the optimization goal, or
yes,
is that
yes.
handled as well?
The user usually prefers to specify the optimization goal, so the overall optimization goal will be given by the user. If the user will not specify, we will just choose our default. So, thanks for those questions. It brings us to the next examples, which will show the entire freedom of choice that we have when we think only of the functional perspective and not of the implementation perspective. So let's look at a quantum adder once again, a very common workhorse in quantum algorithms, because and for all quantum algorithms, most of the effort goes into classical computation within the quantum algorithm, whether it is oracles, whether it is the Shor's algorithm with modular exponentiation, and whether it is HHL. Most of the logic is classical logic. So we need a quantum adder within, we need an adder within some quantum algorithm. So let's suppose 3-bit addition. I don't expect you to really notice the code here. Maybe if you do see this would be the expression written classically, you can just write down any expression classically and we would understand its meaning. And related to the previous question, you as a user can specify the constraints, the overall constraints, can specify the maximum width of your hardware or your simulator, and so on. Or you can specify the optimization parameter, whether it would be the number of CNOT gates, 2-qubit gates, depths, or whatever, D gates. And over here, by the way, you have a comprehensive list of quantum algorithms. For example, the Shor's algorithm you would find here. You would find many applications here and tutorials, but here are the arithmetic examples that we use. And now let's look at the technology part of a 3-bit addition anywhere in the algorithm. So those two guys have the same functionality of 3-bit addition, except that here the result is in place on top of one of the inputs. And here the result is out of place in addition to the inputs. So the technology, the synthesis engine, the compiler, whatever you want to call it, needs to understand first whether the inputs are still relevant down the road, whether we need A and B down the road, and also it needs to understand, suppose we don't need them, whether in this trade-off of width versus depth, it's better to go on less widths, less qubits used in the context of the algorithm, in the specific place where this adder appeared, whether it's better to use less qubits, or whether it's better to use whether we have enough qubits, and then we can trade off depths, because this would be much, much deeper, because we are still in the quantum regime. So in order to free one of the inputs, we need to disentangle the inputs, we need to freeze them, we need to do the reverse operation, and this is very costly. So first, the compiler needs to understand whether the inputs are needed. Second, it needs to understand whether now better to use more qubits even if the inputs are not needed, or whether we are starting on qubits and it's better to pay the cost of more CNOT gates for uncomputation. But this was one implementation of an adder. This would entail, in fact, a ripple adder carrier and a ripple carry adder, just a classical adder. But the same adder, we can also implement it in Fourier space. Then we get a much shorter circuit with other trade-offs. So we see 4 implementations for the same adder. Each implementation may use many auxiliaries, yes or no, because you see multi-control gates in some places. And all those considerations should be done by the automation. Today, if the developer cares also about optimization, they need to very carefully decide which adder to use, whether to free the input, whether not to free the input, and how many auxiliaries to put for each implementation of the sub-function. All this really should be done by automation. Another example, which I mentioned a little bit, is uncomputation. So once we decided to use auxiliary qubits, because it helped us in one part of the circuit, now we need to decide whether we destroy them, whether we uncompute them. If we uncompute, we have more qubits at our disposal down the road for the algorithm. If we do not uncompute, then we don't have these qubits, they are still entangled with whatever service they provided earlier, but we have a much shorter circuit. So this is again part of the decision freedom that the algorithm has. I won't go into this example because it's a little bit confusing, but depending on how you do this computation, whether you compute C or D first or compute this multiplication first, you may be able to save some qubits, provided that you can free them, that it is not expensive enough for you to, or for the hardware, to uncompute. So all those considerations should again be taken into account. Here you see the end result of the expression, more qubits if you compute in parallel. Again, going back to Bettina's talk, that all quantum computation is done in parallel, and I very much sympathize with the idea that you want to be as much as possible a tight box. And here you have a more sparse box. You do less computations in parallel, but you do it on less qubits. So again, a trade-off. And one more thing that I want to again stress, all those considerations are local in the algorithm, depending what you need currently at this point in time in the algorithm. At one point in the algorithm, you may choose this implementation. At another point in the algorithm, you may choose this implementation because even though the constraints are global, how many qubits you have globally and what is your noise level and so on, the considerations locally are very, very local. And you may have different results for different places. Let's go into a little bit of results. I will show some clear results later on. But here you see a full oracle from some example. The same oracle. Oracle meaning some mathematical expression that I've shown in the beginning. This one implemented with 25 qubits, with 36 qubits, the same oracle with more auxiliary qubits, much shallower, and so on. One more consideration is the approximation level. Now here it becomes a little bit interesting and tricky and interesting. By the way, I pride myself in doing the boring stuff, the very, very complex automation, and requires this is with my engineering head of all the knowledge coming from the EDA industry with 60 years of development. But at the top of it, it's the boring stuff. It's taking the interesting stuff from the user and providing the best implementation in all places where the user does not want to care about. But here, still, it becomes a little bit interesting, even from the automation perspective. Because now we have a functional trade-off. We want to approximate, we want to say, do some state preparation function. But we know that we cannot do it exact. But we cannot do it exact for two reasons. First is because the hardware is noisy. Even with fault tolerance, even after we have fault tolerance, the results will be noisy, depending on what deepness of fault tolerance you want. But certainly with NIST devices. But secondly, algorithmically, to have an exact state preparation can be exponentially long. So by design, you want the state preparation to be approximated. Now there is a trade-off with the hardware here. If you do a very exact state preparation function, it will be very deep. Maybe the hardware noise will kill it. If you do it shallow, algorithmically you will not get an accurate results, but at least the hardware noise will not kill it. So here you have a trade-off between the algorithmic approximation that you allow for this part of the algorithm. The user only tells you that I want 66% fidelity for the entire algorithm. Now the automation should decide how to distribute this approximation between the different parts of the algorithm. So now you have an additional trade-off. For this particular part, whether to make it very exact algorithmically, but then the hardware noise might kill it, or whether, anyway, the hardware noise is too large, so why invest so much in making the result algorithmically accurate? So here you start to go into hardware fidelities and hardware calculations of two considerations. And obviously I will not go into those, but whoever is working on noise analysis, algorithmic analysis, and noise analysis, I'm happy to share those slides. And again, you would see that depending on this competition between the algorithmic accuracy and the noise level in the hardware, you would find two different implementations for the same function. And I will skip one more example, totalization example, and I would also skip fault tolerance or error correction aspects, except to say that I totally agree with the two previous speakers that error correction comes in various levels of the design. You can completely forget about it and treat it just as a logical design and let some low-level mechanism put in the error correction, or you can include the error correction code in your design, and we are kind of celebrating these different levels also in our case. So this is how we would treat EDA automation in fault tolerance, of finding the best path where two logical gates can be done at the same timing without crossing each other. So it's another consideration to take into account, how to minimize the crossing between two logical gates, the physical crossing between them. And let me briefly go over the results. Robert, I assume that if you stand up, it means that I will be a little faster.
We have 10 more minutes left, and I really would like to leave some room for questions. So.
Okay, so results are always the fastest part. So maybe we can skip this. All results here are comparison with Classiq, but I'm very happy to get modern results from you guys, and then together we can compare. I cannot say that I'm aware of all the research work that is going about. Typically, as long as you don't use this type of thoughts and technologies, then probably the results would be the same compared to any low-level approach that you take. Those results are interesting because they show a difference in the final result, no matter how much it took. The final results, this would be for VQE for some particular case. So using this automation, you also reach a more accurate final result, a lower level result, a lower energy than was possible with Qiskit. By the way, we've shown all the results to IBM, and I don't think there is any controversy about that. The reason is clear why the results are better, and I don't think there is any controversy here. This would be a particular algorithm, say, QPE, again, one of the workhorses. So with large QPE precision, the depth using those considerations that I told you about, the depth is exponentially better than without using those considerations. Here you see regarding the question that we have, the user can optimize on width or optimize on depth, and you get different results, obviously, with the depth, but they are still would be much better, exponentially better than any approach which does not use these considerations. I could share the same for HHL. You see, you typically very robustly see this exponential better behavior on anywhere you look, and the reason is clear. So I could have shown many more examples. Let's show runtime examples. So once again, you must have anything we do is scalable, meaning that we do not go into at all. It's a rule in our company. The automation algorithms must scale. They cannot be exponential. So here you see this the scale of the runtime here, whereas Qiskit is truly exponential for this particular SAT Oracle generation of the SAT Oracle. We are exponential in this case, but much, much more gradual. I'd like to show you some industrial results. This again, I could go over. You can ask the presentation from me and you will see those comparisons in details. We are an enterprise company. Our users are enterprise. The platform, by the way, is free for non-enterprise use, for non-commercial use. Just go ahead, register and use it. But we are an enterprise company. We are interested in enterprise and government customers. So just to tell you who we are, and those are enterprise results. Very quickly, I will go over this slide, and then we'll forget about the others. But this would be CNOT counts on some industrial result coming from a customer. So first, you see the scale. This is a handcrafted algorithm from the bank. It scales exponentially worse, and this is really handcrafted. The orange ones are truly with the push of a button of Classiq's technology. So first you see again the exponential difference. It doesn't show up very much here, but it is an exponential difference between the results, but much more than that. When I say the bank handcrafted it, it handcrafted the Python algorithm which will reach this point, but the Python algorithm itself is not scalable for the bank, so they were able to reach up to 80 qubits and easily will reach 140 qubits with much better figures of merit of the CNOT. This would be the synthesis time, the time it takes to run, and I will, what is that? And I will leave the file. So I promised you a few words about Classiq. Maybe only the vision. This again, our ecosystem view. What is this? This is the ecosystem view. But let me tell you our vision. Our vision is that when Bardeen, again a physicist, invented this device here, I don't think they ever thought of this device here, and when Russians in this case put this Sputnik into the air, I don't think we would have delivered the pizza for our dinner using this device here. So we don't look for the killer application today. We just believe in the technology, in the quantum technology, and we want to develop it and develop it good and robust and fast. And we do not care to guess what will be the application 20 years from now. And Robert is very, very polite, so I will just show. We are a 65-person company divided between engineers, EDA engineers, software engineers, quantum physicists, of course, and so on. and I will keep this summary online, and I'm happy to take questions.
Thank you, Yehuda.